Hi guys, we're gonna do a quick video on problem 1. We made a change on this problem. We discussed the fact that the force applied by the car on the engine is equal to the force applied by the engine on the car. So that is a Newton's third law pair. And so that's just not really a good way to ask the question. Okay, so we're going to say, what is the drag force? Drag force. Okay, and we're going to say that this car accelerates from rest to 28 meters per second through the air. Okay. All right, so now I'd like to remind you or reinforce to you that we want to do these problems with a certain order of operations. One free body diagram, and annotate the graphs. What does that mean? For us, it means dirt. We'll talk about that in a minute. Number 2, we'd like to have equality statements, guys. That we're going to live or die on equality statements. Oh, that's bad, right? Equality statements. Okay, and then 3, math models. Something is very strange. Maybe my thing is upside down. Hold on a second. Let's see, it's writing very strangely. So let's see. Maybe this will be better. What do we think about this? Ooh, no, now it really is upside down. Okay, thanks for hanging with me, guys. I'm doing this at home in my COVID lockdown. Okay, so let's see what we got. So then last, math models. Okay, great. So that's going to be the order every time. All right, so let's just pick a new color. How about pink? All right, so the first thing we want to do, make a well-labeled diagram. Okie dokie. I've got a car. It's starting from rest. Rest means V naught and X naught are both 0. Okay, so there's the starting line. And then later the car has a V of 28 meters per second. Okay, great. So I think that's probably the car is, traveling this way. Great. All right, so we'll label diagram, force diagram. Okay, so if we're going to do a free body diagram, I think we can know that the FG, right, on the earth, it's too hard for me to write, guys, so I'm going to say the on by language, but I want you to write it. On the earth, on the car by the earth, right? And then we have force normal, balancing with that, on the car by the surface. I'm going to use congruency marks to make sure they're balanced. I'm going to use a different color in the horizontal. So I'm going to have a force here. And we discussed this at length in class, that in the original solution it said force of engine on car or something. And we've talked about the fact that, the engine pushes on the car and the car pushes back on the engine. But what's really true is that when these wheels turn, the wheels, if I say that's the ground, push on the ground, and the ground pushes, the wheels push on the ground and the ground pushes on the wheels. And so it is the force of the ground on the wheels. It's a traction force, right? Traction, we call something traction when it's friction that increases the velocity. Okay, so it changes the velocity in the positive rather than reducing it. So this is the force of the ground on the car that's propelling it to the right. Okay, and then because it says through the air, and I'm going to try to make sure you get this information in class, but if you don't, then just forgive me for not having it initially. Then we know that there's some force drag, okay, which is what we're solving for. Force air, so I'll just call that force drag, okay? All right, so that's great. Let's see, annotated V versus T graph. So what we have is an unbalanced force. So now we need to do equality statements, right? So the sum of all the forces in the X is going to equal M. Sorry, I don't know what's happening now. Let's see. Oh, exit drawing. Okay, great. There we go. Okay. Oh, okay. Well, that's really terrible. Okay, so sum of the forces in the X. So it's going to be, you know, force traction this way, force drag this way. And so that's going to equal the mass times the acceleration in the X. And then the sum of the forces in the Y we know equals mass times acceleration in the Y. But really it's 0 because force normal we know is equaling force G. Okay, so if we go back to this one, we've got, what do we have acting in the X? We've got force traction minus force drag, right? Equals MAX. Okay, so now if we want to, so this makes it good for us. The next thing, what do we want? So we have a net force on this, right? Constant net force, so we're going to have some right here. If I, let's see, so let's see, I guess I don't think I'm going to label this right now because I think it'll make this too long, so the video too long. But I think I could find the acceleration by having good labels on here and just finding the slope of this. You know, if I made the graph match my numbers, or I could say, V equals AT plus V naught, right? And so, I have V and V naught, right? So V naught is 0, so it's just going to be 28 meters per second divided by 20, right, equals A. So we end up with A equaling 1.4 meters per second. And that would mean that the slope here would be 1.4. meters per second. The area under here is going to be the total distance traveled. So if you will take the time to make a good scale, then you can calculate the distance traveled or the slope graphically. Goodness, that looks like a hairy monster. Sorry about that. All right, so there's the acceleration. So that would be what, I? And II, how far does it travel? So if I had good scaling, I could just find the area under, or I can do it mathematically with X equals 1/2 AT squared. Yeah. So plus V naught T plus X naught. And I can leave off that other part of the equation. So X equals 1/2 AT squared plus V naught T plus X naught. Okay, so these two fall away because it starts from rest. So I'm just going to use this equation. And that would make it just be 1/2 1.4. Right, times 20 seconds squared. Yeah, so this is what, meters per second squared. So how far do I travel? Notice I'm having an equality on every one of these. I travel 280 meters. Okay guys, I'm having trouble with this pen, so I went ahead and wrote this out We talked about what's the acceleration. We used v equals at plus v naught. How far does it travel? We used x equals 1/2 at squared. What is the net force? We're just going to say that the net force is F net equals ma. So that's 1,500 kilograms times the acceleration we found, 1.4, gives us the net force of 2,100. Then if we want to find let's see, the force drag, remember that's what we were trying to find, the force drag, then we would say F net, which we just found, equals traction minus drag, right? That's the net force in this x direction, which is the only place there is a net force. So traction would be mu, force normal, which would be 0.3, which they gave us. When they say newtons over newtons, they just mean a unitless number between 0 and 1. 15,000 newtons is force normal, and remind yourself that force normal and Fg are balanced. And so if I know the mass, right, then I know force normal. Okay, so if I know those two, that 0.3 times 15,000 is 4,500. So I'm going to bring this over. 4,500 minus 2,100 is going to give me 2,400.